So the title of the talk is Rholang is simple, but it's not easy. So if you're not familiar with the reference, you owe it to yourself to go spend the hour to watch the talk about where this came from. There's a developer who talks about the difference between simple and easy. So simple being not very many moving pieces, and easy meaning this is familiar to me. All right, so before we get started, we're going to use some definitions. Name or channel, I'm going to use those interchangeably, even though it bothers Dan. If it helps you to think about it, there's a tuple space. You can think about the channel existing there and the name getting you access to the channel in the tuple space object. The tuple space is our storage layer. It matches up reads with patterns to writes with data. And a ground term is a Rholang term that's behaviorally identical to nil, but distinguished, possibly distinguished. It could be nil as well. And the last thing that I want to do is, it's not on here, but we're going to explain what Rholang is. Rholang is a programming language designed by Mike Stay and Greg Meredith that implements features on top of the lambda calculus, on top of the row calculus, kind of in a similar way to how something like Haskell implements or ML implements features on top of the lambda calculus. Okay, so here's the overview. We're going to talk about how Rholang is fairly simple. There aren't actually that many pieces. It's parallel, has a few simple ground types, and we're one of the things we're planning on doing is enhancing that as we get to the case where Rholang is a general purpose programming language. We will treat Scala objects as if they were Java objects or other non-native objects as if they were ground types, and you'll see in a second why that makes sense. Rholang has a fancy match engine, which I wrote, and it uses it everywhere. And then we're going to go through some common user misconceptions and frustrations. All right, so let's talk about how Rholang is simple. It only has a few moving parts. You can't actually do that many different things in a Rholang term. So Rholang has expressions. Expressions are side effect free with a couple caveats, and I'll hopefully, if I didn't remember to put it in the slides and you want to know about them, feel free to ask at the end. You can send on one channel. You can do a receive on one or more channels, and the semantics of that is you either get the receive either takes all of the sends and then executes, or none of them. So it's kind of a way to take two locks at once in an atomic way. If there's time, I can talk about how the structure of names allows us to do that in a way that works. You can allocate a fresh channel, which no one else has a handle on, and which can't be forged. And you can do pattern matching, and that is our sole source of flow control and branching, is the pattern matcher. We have syntax for if-else, but that devolves into match expression with true and false. So it's just syntactic sugar. All right, before we can talk about the sends and receives and the pieces, we have to talk about how names are built in row calculus. And this was one of Greg Meredith's key insights, is that pi calculus depended on two things. It depended on the semantics of pi calculus, but also like some way of describing names, and he wanted to unify them. So in the row calculus, names are quoted processes. In Greg's row calculus paper, he also uses names for variables, and so there's a substitution of names for names. In Rholang, we just use variables for variables. So if you've read the row calculus paper and you look at Rholang, you might get confused momentarily until you realize that that's what we're doing. In Rholang, every name is a quoted process. So you may have heard about unforgeable names. So the way that you make an unforgeable name is to quote an unforgeable process. That's it. So all names are quoted process. You can refer to variables when you quote something. So you can build compound names or derived names in incredibly useful ways. Hopefully I can talk about, if there's time at the end, maybe I could talk a little bit about some of the useful ways that you can derive names. So if you quote a process with no references to variables, then it's guaranteed to be forgeable because you've written down a piece of code and anyone else could write down the same piece of code and quote it. At the moment, there's an incredibly simple typing discipline on the Rholang source, which is that based on where a variable occurs, we can tell if that variable is referring to a name or referring to a process. And you can always, you always take a variable, quote it, and have a process, or take a process variable, quote it to get a name, or vice versa. If you have a name variable, you can evaluate it and run the contents of that process. All right, so expressions in Rholang are fairly simple. We evaluate top-level expressions when they're used in a send or receive. So we evaluate them if they are in the channel on which you are sending. We evaluate them if they are in the data that you are resending. If you have a receive, and there's expressions inside of the continuation of the receive, that's no longer top level. We don't evaluate that. So if you were to perform this send here, the first thing we would do is evaluate the name that you're trying to send on down to 15, and then we would evaluate the data down to 17, and we would execute that send. So if you try and listen, so you can listen on that channel on anything else that evaluates to 15, and you'll get that message. There's a subtle thing with patterns, and hopefully we'll get there with the matcher. All right, so when you sends and receives evaluate expressions, and sends specifically evaluate the expressions in the data that you're sending. All right, so in order to write down a send, you need a channel, either a persistence flag, which we can kind of gloss over for the moment, and you need some data. And the data is one or more Rholang terms. So in order to send and you always send processes, which means that if you want to convey a name to someone, you just unquote that name and send them the process underlying it. There's a subtle asymmetry that you send processes and you receive names, and the reason, it seems kind of annoying at first, but there's a good reason, which is you'll want to send and receive a mix of them, and you don't want it to, you want it to be equally annoying to send either. And so, you send, so in order to send that name, we'd have to put a star on it. But then on the other side, if we were going to receive a value and a name, we would put an @ in front of the value, and you'll see why in just a little bit when we get to matching. And then you would just put a variable name for the name you're receiving. So in order to kind of spread the pain evenly, you send processes and your received names. All right. So a linear send gets used up when it's consumed by a receive, and you can use this to do things like locking. So, and I don't think I put that contract in the slides. Maybe I should have, but you can think of that as whoever manages to read this value, no one else can read a value on that channel until somebody puts something back. So you can use this as, if you always read the value and then in the body you put it back, you can use this as a locking discipline. All right. So in addition to a send, you can also do a receive, which is written for. I probably should have put the syntax. Oh, there's an example. Receive down at the bottom. So this one is probably. So this one would match up to the send that we did on the previous slide. And we're specifically waiting for the value 7 and some name, which we're going to bind to the variable y to come in on the channel that is currently bound to x. And we're waiting for an empty message to come in on z. And then the body can use, inside of those braces, you're free to use y. And the body will not execute until a send on x and a send on z have occurred that match what we're looking for. All right, so receives are the first place that you're going to see a pattern. We can take apart the data that we receive. Like Mike said, they're far more powerful than just being able to match simple things. You can do, since you're expecting code, you can specify a structural type for that code, like it needs to match some API that I'm expecting. So one of the things that has to happen is you have to, a match will not occur unless you get the same number of things. So if you send 2 things, the pattern has to be expecting 2 things. We're going to add a remainder syntax where if you send, you can say, I'm expecting 2 or more things, and the rest will be wrapped up in a list. All right. So we can send, we can receive, we can allocate fresh channels. So new x in P binds a name that is not used anywhere else to the variable x, and then within P, any references to x until it gets shadowed refer to that fresh name. So we could take the so for instance, if that were the body, the receive down there were the body, then x would be bound to that fresh channel. Okay, so the name that's fresh is a quoted process, and this name that you have bound to a variable is unforgeable. So when the code executes, there's a name referred to by x, but you couldn't. There's no way for you to write code that directly writes out a term that's that contains the name x without it being in the body or having received the name referred to by x somehow. The way that we do this is actually fairly simple. In interpreter representation, there's a kind of process that we just don't have syntax for, that we accept from the user. So it's actually really straightforward to have something that you can't create directly. So on the blockchain, you'll be able to look up what the name of x is. But what you won't be able to do is to create a new process that refers to it unless unless you somehow manage to persuade an existing process on the blockchain to send you that name. So this allows us to do object capability discipline on the blockchain. All right. This is my favorite part because what goes on with the matcher is really cool. So all data in Rholang is a Rholang process. That includes things like integers, strings, URIs, and code. So all data is a Rholang process. Most of the things that you want to compute on are what we're going to call ground processes. So the grammar for writing a pattern is the same grammar that you would use to write a process, except that the grammar for writing a pattern is allowed to have free variables in it, things that don't refer, or things that have not yet been bound. It's also allowed to have underscore wildcards, and there's some other things that it will be allowed to do, like we're going to add type signifiers for things like int and string, and you won't be allowed to put that in a top level. You won't be allowed to put those in a top level pattern either, or a top level process. We need to know. You can't just say, okay, we'll run this on some string. You need to know. You need to be specific which string you're running it on. And so the matching that we use in the matcher is the same matching that we use in receive statements to verify, to decide whether or not to fire off a continuation. Except that the patterns for receive are name patterns instead of process patterns. And you'll see, so if you look down there, that's what at 7 is a name pattern, and so is y. So we're expecting a specific name, and then y means I'm expecting an arbitrary name. And whatever name I get, bind it to y. You could put at y there, and that would say I'm expecting a name that's a quoted process, and that process is arbitrary. And since all names are quoted processes, that will always match, but then y would be a process variable. And so within the body, you could use y as a process variable instead of as a channel. All right. So, and the last thing to know, so is that the tuple space has a handle on the same matching code. So you can, oh, I should have written out a match statement. Sorry. So all receives and contracts have patterns. So when you write out contract name and then the arguments, those arguments are patterns, and specifically they're name patterns. We're going to have a remainder syntax for contract 2 as well. Okay. All right. So here's here's an example where we call match directly. So you'll notice that we don't have a with statement, and we don't actually have case quantifiers. So it's not quite like Scala, but it's fairly simple. So we're going to handle 3 different cases. So we're going to match X, and we can expect either an empty list or a 2-item list, and we would bind within that second body, X and Y would be bound to the contents of that list. So it's a destructuring assignment. And as we want to be able to, and if you used something besides X, like a dummy, sorry, you could still refer to X within the body. So, and then this one is an interesting example. You can expect a list of 3 contracts. So you can use this to do things like, well, I'm expecting some API, and you have to give me code that matches the API. And in this case, A, B, and C would be bound to the contracts, listening or bound to the contract, the names that you would use to invoke the contracts in X. So you could do something like, within the body, you could do x.nth0 pipe a send 2 arguments, and it would invoke that contract and send those 2 arguments to the piece of code that you got. And one of the things that we actually want to do is we're going to implement confinement, where you take a Rholang process and you rewrite it so that it no longer has any ability to send to the outside world. And then, so it does that by rewriting all the free names in it to fresh names. So here, A, B, and if we had done that already, and A, B, and C would be fresh names, we would have a handle on A, but we would know that if we invoked A and sent it some arguments, it would have only the authority that we gave it via those arguments, and it couldn't do anything else. All right. So, enhancing the ground, also known as fertilizing. So, in the row calculus paper, hopefully some of you have read it, but the only term that is not defined in terms of other Rholang terms or names is nil. It's 0. And so it turns out that allows you to build an infinite number of terms, but we wanted to be able to have terms that were side effect free, basically that acted like nil when you put them in parallel, but you could do things like a quality comparison or arithmetic with them and get different results. So the main things you can do with these terms are matching and other expressions, basically computation on them. So we can also turn processes into ground terms by putting them in a collection. So if you have a list and you put it in parallel with something in your, at the top level, the list has no side effects. But if you use either a match or a method call to pull out the contents of the list and then evaluate it, then that thing that you pulled out, you can put that in parallel and it will have side effects. So yeah, the list with one item has no side effects. Even if you were to unwrap it and put P in, then P would have side effects. And there are currently a bunch of things that we consider expressions, and we treat variables and method calls differently. In that, if you put any other expression in parallel, we just don't evaluate it. So if you have x plus 7 in parallel, we just aren't going to evaluate it because we know it's either going to be an error or it's going to evaluate to at the moment we just have integers. It's either going to be an error or an integer. And at the moment, what I'm leaning towards in the error model is that errors just reduce to nil. And so it's just going to have no side effects. Okay. So, that's basically what you can do with Rholang. But it's not like things that you might have seen before. So the question is, okay, well, you told me how Rholang works, but how do I get stuff done? And so this is where the not easy part comes. And what I mean by that is that it's not like Java. It's not even like Scala or Haskell, because in order to, you have to start thinking in a slightly different model in order to think about how you're going to get things done in Rholang. All right. So everything keeps happening all at once. So in order to make things occur in a particular order in Rholang, you have to have a data dependency between them. If you don't, there's no guarantee that you can force things to be in order. So Rholang does not have a semicolon. Instead, it has a pipe. And so P pipe Q implies running P and Q at the same time. So one way you could do this is non-deterministically choosing between doing P first or Q first. But you could also try, if you have a computation model that supports concurrency, you could just be doing it all literally at the same time. All right, so how do I how do I force something in order? So there's a pattern that you're going to want to use in order to force, things, A happens, and then B happens, and then C happens. And those of you that have written like callback-based Java are probably actually familiar with this pattern. So in Rholang, you can make a contract or a receive that acts like a function. And I'll show you an example. So we have, in the current Rholang interpreter, we have the ability to print things to standard out, and they actually, it dumps the protobufs at the moment. We're going to try and clean that up. But you can write out output. And you can wait until the output has finished and before writing out more output. So in this example, we would print out hello, then we would wait on the ACK channel until a message arrived, and then we would send and then we can send a message without waiting, because we just want, the only thing we want is that hello gets printed and then world gets printed. So we don't since we have nothing to do when world gets printed, we don't have to wait. If we wanted to print three things, we could reuse ACK and say standard out ACK, bang, and then inside the body do for something from ACK and then print the third thing. So those of you that are familiar with like callback disciplines, this is what you do. And in order to make something act like a function, you have to pass in a return channel, and then you have to have a separate receive that says, okay, when something comes back, this is what I do. And that's how you would translate things that are like function-based and would follow a function discipline into Rholang, is you would use a return channel. You would make sure that all of the evaluation paths through the body put something back on that return channel. Or if you wanted a partial no return function, you could make it some of the time put something back on the return channel. All right, so let's talk a little bit more about the matcher. It seems so that until you get used to it, the matcher is going to feel a little weird, and that's okay, because once you get it, you're going to go, "Wow, I really like this." So one of the things that Mike and I realized was that we could make, in order to make the grammar simple, we could make the grammar for top-level processes the same grammar as the grammar that you use to write down patterns. And then we could just check when we're doing the syntax translation that what you wrote didn't have any free variables or wildcards. There's some other things, when I get to the roadmap, there's some other things that we're going to add that you also can't put in a top-level process. But it's simpler to make the grammar regular and do the check at compile time than it is to try and make the grammar have a distinction between a Rholang process that can have free variables in it and a Rholang process that can't. Or they can use wildcards and it can't. Or it can use, it can refer to things like int and string, or one of the things that you won't be able to do is use logical connectives in your top-level term, because you can only write, instead of, if you view the patterns as picking out a set of Rholang terms, then the top-level pattern has to pick out exactly one Rholang term, specifically the one you're trying to write. All right, and I'm sorry for this one. Rholang is a work in progress, and so at the moment our Our error model is it's not very good. So one of the things on our list is to work out a specific error model where we have the semantics that we actually want, instead of just killing the entire interpreter when we find an error. I mean, it is a valid error semantics. It's not a very, it's kind of user hostile one. And it won't work very good, it won't work very well on the node. So, I'm sorry, but on the other hand, this is a programming language that, is brand new, and we're trying to make it work. So one of the questions people have asked is, it doesn't have any way of interacting. So at the moment, we have the ability to write things on standard out. We have a REPL. The REPL only accepts Rholang terms that are a single line. Sorry. One of the things that we're planning on doing, though, is as the node software, the node software will allow you to fire up the same tuple space. So you can write a bunch of snippets and then run one file, and then run the next one, and then run the next one. So that will at least alleviate a slight pain point. If you want to understand how we're going to do the foreign function interface, you can go look at the how we do standard out and standard out ACK. They're both good examples of how to do return discipline for the foreign function interface, and how to take something and make it, or how to produce the right kinds of things to put something in the foreign function interface. So it's not an FFI in the sense that like you just load up a jar and say, well, these are the right things at the moment. But like if you wanted to, but you can add code to the interpreter in the right place, and then have more foreign functions available. All right, and let's talk about what we're still working on. So we're going to have polarity of names and IO pairs, logical connectives. I think I mentioned those. Basically, the ability to say, well, it has to match this pattern, and it has to match that pattern. So logical connectives. At the moment, we have really good support for lists, and we're working on set, map, and tuple. We'll have the distinction between lists and tuples will basically be that we will have methods that make it simple to functionally modify the contents of a list. So if you have x.append some more list, then it will, the result of that expression will be a longer list, but x will still refer to the short list. But we intend to have sets, maps, and tuples, and they'll behave functionally. And and a channel discipline. And so we plan on having a typing discipline for channels, so that you can verify that you get a channel that where the user has basically promised to send specific kinds of things, and then that allows you to make sure that like what you're expecting on a channel is something valid to receive, and it allows you to do a lot better type enforcement, that your program won't crash and burn with type errors. All right. So I should have put up a question slide, but
thank you.
Go ahead and take questions. Yes, go ahead.
I can imagine wanting to write code that says this contract will take a process or code that will only speak on one or some given set of channels. That it might be really complex, there might be tons of code there, but I know that it doesn't speak on any other channels but this, or send on any other channels but some small set of them. So
you're going to want to talk to Mike. That's more of a behavioral type, and we're not planning on doing that for Mercury. But one thing we are planning to do for Mercury is that you could take some piece of code and you can write it so that it can't speak on any channels, and then give it the two channels that you want it to speak on. So you can proof by construction instead of proof by examination, that it can only ever speak on those two channels.
Kyle, If I understood correctly, you talked about the asymmetry between sending processes and receiving names as being to make it nicer, to not have to quote everything everywhere. Could you speak a little bit to that and say, maybe give some idea of what the alternative might have been?
Sure. So there's three obvious alternatives, which is you always send and receive processes. You always send and receive names. Well, there's four. You could always send names and receive processes, or you always send processes and receive names. So in the row calculus paper, they send processes and receive names. So there's at least some precedent. Another option is that you can send both and then you try and guess on the other side what it is. It doesn't work very well with patterns because if you have a free variable, what is it? Are you sending a process or are you sending a name? So I think that the asymmetry that we have works out pretty nicely. Mostly because on receive, you can just write down what it is you're expecting. So I think it's pretty straightforward.
So I think you said that if you do the new connective, then you create a new name, which is an unforgeable process.
Yep. It's the name is a quoted unforgeable process.
So what process is it? Can I run it? And then what happens?
Sure. You're welcome to run it. It's a ground term, so it's equivalent to running nil. It's like running 7.
Okay.
So you can actually think of it that's a very good way to think of it. It's just like a wrapper that says, at the moment it's a wrapper around a string, but it's just labeled, it's basically a tagged string that says, okay, this is a private name, and the contents is this string. So yes, you can run a private name. And that's behaviorally equivalent to nil. So if you have new x in star x, that will compile, it will run, it won't do anything.
Yeah, if I allocate a new situation as described, and I call it Kyle, and I hand it to you, and we restrict it in all these ways we've just said, can anybody expect to observe what goes on that channel, or is it restricted? And it's only you and me.
So it's on the blockchain. Everybody can see what happens, but only you and I can make anything else happen.
We are the only ones who can use it.
Yeah, we're the only ones who can use it.
So what exactly is the difference between Rholang and just the pure row calculus?
Sure, I can talk to that. So you can view Rholang as a sequence of enhancements to row calculus. So the first thing that you would add is the use of variables. So you can add, row calculus with variables would be straightforward to model. Then you can have row calculus with variables and interesting ground terms and some expressions. And that itself would be also fairly trivial to model. Then you can add, row calculus only has single receives. So you could model it with, then you could add the join semantics, where you can either you can receive on multiple channels concurrently. Let's see. Oh, and then we have, row calculus does not have the patterns, the pattern matcher. So that's another thing that you'd have to add in. I said join. And then any typing discipline, including name polarity, which are things that we still haven't added to Rholang, you have to add those to row calculus too. All right. Go ahead.
Yeah, sorry. I realize I'm asking you something you might not be prepared for, but I'm going to do it anyways. Is there any chance you have a non-trivial example of some Rholang you can show us and walk us through? Something more than hello world?
I do not, due to technical difficulties. So, they're on here, but here won't go there. Sorry. Yeah, maybe I can do that. Well, it's non-trivial, so like you can either see it or read it. You ask. All right. All right. So there's contract make code check, and that would probably be running on some registered name instead of on just some. This is just a demo. So this is where the interesting stuff starts happening. So contract make code check. It allocates some new channels, new port table. And then we have patterns. So if you send new along with an argument and an ACK channel along port, we will do the following. We'll construct. We'll give you the ticket, and we'll hold on to arg by creating a write at the compound name ticket star table. And table is something that it's unforgeable. We haven't let it leak. And so if you put something, so you constructed a name, it's a compound name that requires two parties to cooperate to build it. And so if you execute new, then something is sitting at arg, or sitting at that compound name, specifically arg, waiting to be consumed. So then you turn around and you write a get to that port later. Then that also sends arg, which is it's not the same arg as above, but it will be the ticket that we gave you before and the ACK channel. And so we do a linear read we try and take the value and we try and take the value from the compound name that should match up. If you set ticket back, you'll get the same value out, and then it will be consumed and gone that you put in the code check. And then set is like, it's an atomic version. It allows you to swap what code you have in the code check. And if you look, that's exactly what's happening. We read from the compound name. We update then we put, so that consumes the write at that compound name. Then we put a different write at the compound name, and then we return true. You could very well make set return you the old value, and in order to do that, you change that underscore to at old val, and then instead of ACK bang true, we would send ACK bang old val. So that's basically a code check. Go ahead.
What does the underscore do?
Okay, so underscore is a pattern that matches everything and doesn't capture anything. So in this case, it would be the same as for x from that, and then we just don't mention x. They're not structurally equivalent, but if you have a process that never mentions x, it's behaviorally equivalent. Inside of processes, there's a subtlety, and I'm going to walk over to the board and I'll explain the subtlety. So, if So, right, like we get these two patterns are not equivalent because the underscore, placing an underscore here will match strictly more things than placing P here. At least at the moment. Because if P refers to X and we try and pull that out, well, now you have a term with a hole in it. And we're still thinking that we might be able to model a term with a hole in it so that you could capture it, but you couldn't use it directly, right? Like you'd have to say, well, what do you want X to be? Because if P refers to X, then, but if P does not refer to X, then P will get captured. But the underscore can refer to X because we're not capturing it, we don't have to know what X is. We're just going to throw it away. So they're not exactly equivalent, but at the top level, so every pattern is a process. So this is a top level wildcard, and a top level wildcard is as powerful as a top level variable. So that is a receive on a single channel. There aren't actually any joins in this code. A join is a name for a receive on more than one channel. There are 4 arguments expected from the read from port, and so that's the number of arguments is included in the patternness of whether or not a read matches a write. So that's a pattern that's expecting 4 names to come from port. And the 4 names have to be exactly the quoted string set, an arbitrary name, arg1, which is a quoted process, or a quote of arg1, a quote of arg2, and then the name ac. And the reason that you do that is because you're going to use arg1 and arg2 as processes in the body, so you don't have to put stars all over. And you're going to use ac as a name in the body, so you don't have to put at everywhere in the body. Okay. So you could get rid of the ats. So there's some equivalences things that you could do. So we could get rid of these ats right here, and then we can make equivalent code by putting stars right there. And similarly, if we wanted to, we could put an at right here and an at right there. In terms of style, I think that if you're going to use something as a process, put an at in the receive. And if you're going to use it as a name, leave it as a name.
On line 29, there's a compound name. Can you tell us about that?
Sure, that's a compound name. Like I said, you can refer, when you quote and when you build a name, you can refer to a variable. And the nice thing is that compound names are super powerful because I give you half of the name, and in order to construct in order to get the data back, I never let this leave.
Parallel there is not parallel. The pipe there is.
No. The pipe is parallel. You've quoted a process. So you just build a compound name. You could use list in this case. You could build a list of argv1, comma, start table. So parallel has the nice property that if you take, that it is symmetric. Yeah, it's commutative. And so if you want, like if you're trying to build a name where 5 of us work together to build a name that that all of us know, right? Like then, using par is simpler than trying to figure out, well, who goes first and who goes second and who goes third. It's just convenient. That par is never going to be evaluated and produce effects in parallel. It's just a... So the compound name is like a set of names? You should probably use the mic. So the question was, the compound name is a set of names. So what we're doing is we're using names to produce a larger compound name. You can build them out of any Rholang term that you want. It's probably bad style to build anything other than parallel names or sets or lists. And the answer is no, it's not a set, it's a multiset. So if you have 2 copies of the same name, it's not equivalent to 1 copy of the same name. So it acts like a multiset. All right. If there aren't any other questions, we can wrap up. I'll be happy to answer any questions you have offline. If there's Rholang you can't get working, and it keeps throwing errors, well, patches are definitely welcome. But I also want to help you be able to write code and get a feel for what it's like to write Rholang. So, all right. Thank you.